good morning, everyone. My name is Eija Honkavaara, and I work as a research professor at Finnish Geospatial Research Institute at National Land Survey Finland. And today, I can say that our research and our part in this RESDiNET project has been about remote sensing technology. And in my two presentations, I will talk from quite technological point of view. So we are developing new technologies, and then they are applied in different applications. And this bark beetle management has been a very important application field for us for several years, and we have made nice progress in this field. And we made small changes to the topic of the presentation. So topic is absolute calibration in drone imaging spectroscopy, consistency across time and space. And this presentation will be given by myself and Juha Suomalainen. So Juha will soon start speaking. Then I'm trying to change the slide. It's not working.
It's not on.
Okay.
Sometimes the first step needs to be done here.
Okay.
Now back. Now it should work.
Okay. Yes, and this presentation will contain a lot of scientific details also. So about why we are interested in this topic. So we are talking about multi-year and multi-season drone datasets, which they are giving nice opportunities for environmental and ecosystem monitoring, like from geometrical and structural analysis, we can reveal many spatial and physical ecosystem changes and properties. Radiometric analysis gives us some spectral and biochemical variations over time. And when we combine geometric and radiometric information and analysis, we will get really incredible information about the ecosystem responses to environmental factors and many topics. But anyway, when we are analyzing this kind of image datasets, this all analysis, there are disturbances due to many geometric and radiometric inconsistencies. The geometric misalignments and challenges, they are quite well already solved. So there are state-of-art solutions for that. But radiometric calibration is still a big problem. We really need to transform image values into physical surface reflectances and remove all possible disturbances from the data in order to be able to compare data across times, sensors, and sites, and to get absolute knowledge about the environment. So when we are capable to do this, then we will be able to do reliable analysis in time series and also across the sites. So here is why we need this corrections, some examples. You can see here one case when we have been collecting data. So there is a orthophoto from agricultural field. It has been collected in varying conditions like cloudy, sunny, and so on. So you can see many, like here is a change from cloudy to sunny, and then there are also different levels of cloudiness, so that there are many disturbances in the data. Also, when we are collecting data in different, like in sunny conditions, there are also many disturbances. So the data is not quantitative if we don't do anything with it. And there are like important factors what we need to correct are related to atmosphere, illumination, object, and sensor and system. And we will be talking about this soon. So first of all, the first fundamental challenge is this reflectance anisotropy, so that when sun is illuminating one direction and we are viewing object from another, it's always dependent. The reflectance value what we get, it is depending on these directions. We are calling this bidirectional reflectance distribution function that models this phenomenon. So this is something what we need to take into account. And then also, of course, in different conditions, there are always different illumination, different atmosphere. We need to take care about this also. We have there is like from old and traditional remote sensing, there is a quantitative correction chain that we must apply in order to remove all these disturbances. Like we have to correct the sensor errors, the first step. Second thing is to transfer the these digital numbers, the gray values, to sensor radiances. Then we need to do some atmospheric correction. Then we have to make ground reflectance transformation to remove effects of solar irradiance. Then there is this BRDF that we need to correct. And after all, then we will have all kinds of shadows and these kind of things. So everything has to be corrected. So the first two steps here, there are like laboratory calibration is taking care about that. And then about correcting these atmospheric effects and irradiance effects. So there we can use, like, we will talk about this later, but about irradiance data or atmospheric modeling with different radiative transfer model codes. And then we need the PRDF models. So many things to do. So the first thing was this physical correction, where we model everything, and then quite typically we are using the empirical line-based method. So this is the second approach. So we bring some panels in field, and then we start correct many of these errors into one this empirical line equation, and then we are quite happy. Juha will now, I think Juha will continue about empirical line method and all challenges related to that. So Juha.
Yes, first a technical thing. Online we are not seeing the presentation screen, but we are seeing the PowerPoint screen. So basically, we are seeing the first slide all the time. We don't see any sixth slide or something. Can something be done to that? Yes, this is perfect.
Let's see if it changes.
Yeah. Okay. Yeah. Eija already talked about, let's say, that what. Yeah, it looks good. Eija already talked about this like wider picture of all of these issues, but my part is more about this one very specific. So the starting point is the empirical line method. So basically, it means that we have these panels, two or more panels of different brightnesses, and using these we can convert the at-sensor radiances to at-target reflectance factors. And the math is not that complicated, but it requires knowing the panel reflectance factors very accurately. And what makes this more complicated than it sounds is that the panel reflectance factors are not constant in all conditions, but they differ with changing solar zenith angle, but also with blue sky conditions and with the overcast conditions they are totally different. So this is something that if we want to get into high accuracy reflectance factors in the end product, we need to know the panel reflectance factors in any atmospheric conditions. Next slide, please. Yes, and the starting point for this is knowing the BRDF, bidirectional reflectance distribution function of these panels, and as I already said, the reflectance of these targets, it depends on the direction the light comes from and the direction the light reflects to. And this is in an ideal case where we have a light coming as a laser light from one angle and observer is in exactly one angle, then this is called BRDF. But it gets more complicated because the actual natural illumination, it's not unidirectional, but but on different wavelengths, the light comes different from different angles, and there's a diffuse component in the light in different way. For example, on the right, you can see the spectral panel, which is like the most common reference panel used in field spectrometry. Then how that BRDF of that differs in different view angles. And then as a different example, there's like example for a snow with some icy layer on top, which is then like a forward scatterer. And these effects vary in different targets differently. Next slide, please.
Let's have a look, because I was doing something, so now it works.
Yes. Yeah. So in the natural illumination then is that is a combination of the direct light from the sun, or can be considered to be combination of the direct component of the light that depends on angle of the elevation or zenith angle of the sun. And then the diffuse light, which is then in, for example, in blue sky conditions, it's this Rayleigh scattering blue spectrum, blue light coming all over the sky. And or if you have some clouds, then the spectrum of the sky and angular distribution of the sky will be different. So in practice, this direct to diffuse ratio changes with the wavelength. And the technical term, so the where the light came from one direction and observation was in one direction, that's called BRDF. But then in a wider scale, when we're talking about this diffuse light also coming in, we are talking about hemispherical directional reflectance factors then. And this is the basis for what we will going to be doing next. So next slide, please. So then to take this illumination condition into account in the mathematics, then we need to know what is the angular distribution and spectrum of each of these irradiance components. And for this reason, we have run Libra-Tran simulation, and that is a simulation that outputs the direct and diffuse irradiance spectrum, and also the angular distribution of the diffuse radiance. So for this purposes, we have run simulations on two different conditions. So one is for the blue sky conditions, and then the other one is for overcast conditions. And on the right, you can see on the top, there's something on top of my yeah. On the top there's the direct and the spectrum of the illumination or of the irradiance separated to its direct and diffuse components. So the solid blue line is the direct component in blue sky conditions, and the dotted blue line is the diffuse component of the irradiance spectrum. And then the black lines are similar things for the overcast conditions. And notably, there's no in diffuse illumination where you have clouds. In overcast conditions where you have clouds over you, there is no direct component practically at all. Then the bottom graph there, that is showing the results for how is the diffuse component distributed in different directions that the light comes in. And in that one, I think the most notable thing is that the angular distribution varies totally between the different wavelengths. So in the 400 nanometers, which is in the blue end of the spectrum, you have a lot of this low angle light coming in, and this is different on all wavelengths. And this is only showing like the wide spectral bands, but it gets more radical even when you go into narrow spectral bands of the atmospheric absorption bands. Next slide, please. Yeah, so basically, if we now know the angular distribution of the illumination, then this is our our process for calibrating our panels that we use in the image calibration. So basically from the Libretran simulation, we can get this angular distribution of illumination, and that's something that we run for basically all different solar zenith angles. I think we run it every 2.5 degree solar zenith angle. But then to actually apply this for our panels, we will need some laboratory measurements of the BRDF of the panels. So we can have a next slide of that, and we come back to this in a moment. Next slide, please. Yeah, so what we have done is that we have taken all of these, our panels to our laboratory, where we have this goniometer. So this is it's called FCI Space Goniometer. It's developed by Jouni Peltoniemi at our institute. And using that system, we have taken some BRDF measurements of the panels. So the graph in the bottom, that shows basically the measurement scenario what we had. So we just illuminate a spot on the panel using a collimated light source. It's white light, not laser, but white light source. And then we take a range of measurements from different view angles around it. So this is very minimal BRDF measurement that for quite ideal targets can characterize the reflectance properties or the BRDF properties of the panel. But let's say it would be better to do this measurement with more illumination angles and stuff like that. But this should be enough for at least a quite decently accurate BRDF model of the target. And yeah, so basically what we collect is that we collect from different view angles this reflectance factor spectrum of the panel. And with this we can go back to the next slide, please.
Next, previous, next.
Next one. Yeah, it's duplicated. Yeah, so basically now if we know the panel BRDF, we can fit a Rahman-Pinty-Verstraete model allowing to this data, allowing to have like a easily numerically interpolatable model of the BRDF. Then basically we can calculate, use the angular distribution of illumination and this BRDF model to resample the BRDF measurement to this outdoor illumination irradiance. And then to make this model easily usable, we can again fit another RPV model, BRDF model to the data, so we can evaluate that model easily. So basically, we can then save the calibration of each panel in each illumination condition to an ASCII file that is the calibration file for it. Next slide, please. And then what we have done for this is that we have packaged using these calibrated panel BRDF models or HDRF models to Python tools. That's for our most of our internal use called SpecFo tools. And in this using these tools, we can calculate the reflector spectrum for each of our panels at any illumination condition, at any solar angle, and at any view direction. And basically, it's rather simple. We just need to define all of these, and then we can evaluate the reflectance, the BRDF model, and retrieve a reflectance factor spectrum, like you can see in the center in there. Next slide, please. And then I can show you some of the examples of what the results are. So these examples are for this 99% spectrum panel. So this is the white panel used in most field spectrometry. And these results are in blue sky conditions and with solar zenith angle of 75 degrees. So only 15 degrees above the horizon, so very low. On the right, you can see this reflectance spectrum graph. In quite many people who do field spectrometry, they assume that the reflectance factor of the spectrum panels is the ideal white. So it's always this just line at 1. I have also done that in the past, and that's because it's easiest to do that, and it's quite accurate. But then the next step, what people usually use if they don't do that, they use the manufacturer's calibration data. That's something that usually comes with the panel as a USB stick or a printout. And this is then a bit more accurate. It brings some of these like spectral shapes of the panel into the spectrum, but still, this is not really accurate. This is only valid in very specific calibration, illumination, and view angle geometry. And this is not representative of any outdoor conditions. But so from our calibration, we can actually now, the blue line is what our calibration shows that the reflectance factor spectrum of this panel actually is in these conditions that I mentioned earlier. So firstly, you can see that it's definitely not on the same level of reflectance factor of 1. It has this in the blue end. It's much brighter than in the longer wavelengths because of the Rayleigh scattering. So in the blue end of the spectrum, you have lots of diffuse light in that end. So it's more closely resembles to the diffuse reflectance factor of the panel. Then you can see these noise-like effects showing up in the spectrum, but they're not noise noise in our measurement, but these are actual reflectance effects. These come from atmospheric absorption of light at these wavelengths, and on those wavelengths, again, the diffuse to direct ratio in the illumination is totally different than around them. So basically, again, on those wavelengths, you are seeing reflectance factor that is no longer in the BRDF, in unidirectional illumination type, but it's more in diffuse illumination conditions. Next slide, please. Yeah, and then the other big thing is the effect of the solar zenith angle. So again, in here we have the same spectrum panel, but now in this graph we are showing the reflectance factor of the panel on different solar zenith angles. So this is every 15 degrees the solar zenith angle, starting from 15 degrees from nadir, so almost sun above you, up to very low, and this is looking straight down to the panel, and you can see that the reflectance factor of the panel actually varies a lot. So there's something like plus minus 7.5% errors from the ideal if you ignore the solar zenith angle. So this is definitely something that should be taken into account in panel calibration. And basically, this is now a tool that we can use in our field spectrometry to do more accurate reflectance factor spectrum, field spectrometry reflectance factor measurements, but also something that we apply to all of our panels in the drone operations, so we can produce also the drone data with higher accuracy. Next slide, please. So this is just summarizing the basically what I said earlier. So basically, the take-home message is that the outdoor reflectance of targets, they differ from the lab condition spectra, and you have all of these like the spectra distort in many ways. There's the Rayleigh distortion. There's atmospheric absorption band noise-like like effects, and there's lots of level shift things. And these effects affect all panels used in calibration of remote sensing data and field spectrometry. And this is something we are preparing a journal article on. And in that, we will include the Python codes and calibration files for the common reference targets that we have measured. So this is all that I had to present. So back to you, Eija.
Thank you, Juha. So as you see, if you are using empirical line method and panels in field, so this current approach, there are many challenges, and we can see those in images. And of course, this is quite nice approach using empirical line method if the illumination conditions are stable. At least in our cases, we are always collecting data when it's possible, if it's not raining and so on. So weather conditions can change from sunny to cloudy, and so that is another challenge what we are facing. So we are also working and trying to develop something, because it seems that current software like Megasense, this Akisoft, it doesn't correct all the errors. So this is actually quite old thing what I have been developing more than 10 years ago, but now we are taking it back because we have noticed that in many cases we can't correct the data efficiently without making some, or it's very difficult to correct the data to uniform mosaics and eliminate all the illumination impacts and so on. So we have this kind of a radiometric block adjustment method. So when we are collecting normal drone data sets, we are always seeing the object from many different directions. And then the question when we see the object from different directions is that why the digital number is not the same from all directions. And we can actually model different physical phenomena that impact this reflectance when it's going to the sensor. And yeah, so we are modeling that, and we can solve these model parameters using different optimization technologies. And when we have the parameters, then we can correct the data, and hopefully we can get nice results. Here is one old example about this. This is the image what I showed earlier. So this data set has been collected in sunny conditions and during several hours. So these are actually the BRDF, or this reflectance anisotropy effects, what we can see here between the flight lines. So when we see the sunny and cloudy shaded side of the images, so this is the impact. So this method, for instance, was very good in correcting these impacts. So actually we are now developing this further. Here is one example from our current data sets. So this was like collected in shady and sunny conditions, and with our radiometric block adjustment software, we were able to correct it. Megasense, Akisoft Metashape process did not correct that well. And then another thing what you has been also developing is this irradiance spectrometer. So here the idea is that we have on board drone, we have the calibrated camera, and we have irradiance sensor. And if we are observing the irradiance coming from sun, then we can use very simple equation, radiance divided by irradiance multiplied by P. So that gives us reflectance. So this is also something that is being developed at our institute. Yes, then a few real data sets and what kind of problems we are facing now with this data. So our bug beetle research, we have these test areas in different parts of Finland, so southern Finland, Ruokolahti and Koli. So you have heard about these experiments, and here are the data sets that we have been collecting with our current sensor systems, RGB, multispectral, then hyperspectral AFX10 and AFX17. In Paloheinä, we have like 6 years time series, and from Koli we have 3 years time series, and we have really like collected 12 data sets, 16 data sets, and so on in different years. And in total, there are from Paloheinä, we have 100 20 datasets about and call it 22, and we are really trying to get, because they have been collected in many different conditions, and we try to make it qualitative correction. So we have been struggling a lot with the datasets. I've marked with green the datasets that have been somehow processed and analyzed. Others are under processing. So here is one example of when we have been using for some 23 datasets this empirical line method, what I was just explaining. So what we can see from here is a infested and healthy tree time series. So we can see that when we make this empirical line correction, there are still a lot of variation in the data. Here is like another example when there is a tree with like in sunny side and then from shaded side. So the like reflectance spectra, they are really changing a lot depending where we are looking them and at the time. And of course, one important factor here is that the irradiance is changing. There can be shaded condition and so on. So in our current analysis, we have been using normalized data. So that gives us quite nice normalization. So like we can see here is the, I think, healthy tree. Actually, healthy tree is blue, and then dying tree is red. So it gives very nice normalization for the data, and it has been worked nicely in our recent studies. Still, we are really willing to have this absolute calibration. Here is also like when we are then looking different indices, here is this photochemical reflectance index. So this is like a for healthy and dying tree in shaded and illuminated conditions, how this PRI evolves during the summertime. So here is the like this dying tree. We see clear drop at some point of time. Here is after 15th of June. And then the healthy tree is somehow up the whole summer. But this is still, we are working with the data and trying to make this calibration nice and understand how different calibration options impact. And here is then for multispectral for one vegetation index. So here we have a 2 years data set from 23 to 24, and there are some healthy trees and then infested trees. So we can see, actually, it's interesting to see that like springtime, we have the rising reflectance, and then it's decreasing due to the phenological effects, and then yeah, all these indices, and then we see the dying trees, and then some of the trees are like dying later in the summer, so then they are dead in the following summer. And then here we see again this phenological effect. So yes, of course we can see a lot also from this vegetation indices, but yeah, question that how we can we do it better. So about our ongoing research in this topic, so we are first of all working with data correction, like spectral tools, what Juha was presenting, our RADPA, radiometric block adjustment. It is developed in another project for aircraft and then also for drone imaging. We are also testing this DRACOR software. It is a commercial software for hydrospectral image correction. And of course, this irradiance-based correction is one of the topics we want to make better. Then, of course, this adaptive analysis is also one approach. So there is this domain generalization that can, like, from deep learning methods, you can separate object and environment related features. So there is also one paper by Emma about that. So yeah, this is also one very interesting approach, and also different deep learning large language models and also simulated data sets. So there are many opportunities, and we are actually working with all these tracks. And this spectral tools paper is one of the RESDiNET papers that we are preparing, and also this Emma's paper. I can share you our literature if you are interested in more details. So that was all about this. So this was this hardcore remote sensing theory for you from FGI.